for our conference is Roman Bezrukavnikov from MIT, and he will tell us about derived Cartier transform, derived subtitles, and cohomology. Thank you very much.
Thank you very much. Thank you for this opportunity to connect, even if virtually, and to give this talk. I will be describing some constructions in geometric approach to modular representation theory and related constructions in local geometric Langlands duality. And well, this is a conference in arithmetic geometry, but my goal in this talk is to convince people that these subjects provide some interesting questions and perhaps constructions which are interesting for should be interesting to a geometer. And if I do not succeed in this talk, you will have to invite me for 2 more conferences, and then I'll keep trying. Okay, so let me start with just for a few minutes to be in a general setup. So let's be a smooth variety over K of say algebraically closed of characteristic P. I will start by just recalling the setup of the famous Lineage work, which say that Derived cohomology of X isomorphic to Hodge cohomology if under some condition leads to the second with vectors. And so I will recall, so in the form of August Vologodsky, so it says the following. So the argument is this. By definition, Derived cohomology can be rewritten as a certain X group from the in the category of crystalline D modules. So dx is the simple-minded sheaf of rings. So sheaf of crystalline yes, I'm not, so there's a question in the chat. So yes, there's no lifting of Frobenius, but yes, I may have maybe sloppy about things in the future. So let's be is large enough. It is not my ambition to make these things very precise here. Yes, sheaf of crystalline differential operators. Yeah, thank you for this correction. So it's just generated by functions and vector fields subject to the usual relations. Okay, so this is the way to rewrite the left-hand side, and even more tautologically, the Hodge cohomology, which is cohomology of the sheaf of forms, is X from or X to or X in the category of coherent sheaves on the cotangent bundle. People sometimes fashionably called Higgs fields. And now to pass from one picture to another, we can pass from one to the other if I mean, not if, but just using, so via what Vadim Vygotsky and Arthur August called the Cartier transform, which is a functor from, it's not defined on all such things, but from some, I mean, full subcategory. Sorry for the sloppy wording, some D modules to Higgs fields to quasi-coh of T star X. And technically, I mean, to be completely correct, I need to write here T star X1, but again, I'll be sloppy about those things. And so, yeah, so the way I like to think about it is the following. So in fact, so to define it, observe that we have this P center phenomenon that in fact Fp, and then if I have a vector field, I can take it to the power P and subtract the restricted power lie in the center of Gx, and this leads to, well, and moreover, well, the center of Gx is isomorphic to the sheaf of functions on the Frobenius twist of the cotangent bundle, and Gx is an it turns out to be an Azumaya algebra. Over T star X1. So, moreover, this Azumaya, the restriction of this Azumaya algebra to the zero section so this restriction splits. In fact, just the action on the function provides the splitting. So you can say that Frobenius star O is the splitting bundle. If only, if it was true, which it is not, if it was true that the splitting extends to, well, ideally to the whole cotangent bundle, which is pretty much never true, but, well, okay, T star X1, never true except if the base is a point. Or at least to the formal neighborhood. of X. Well, I will drop Frobenius twist. So this will be the case in our examples, but probably this is quite rare. And in fact, it would be nice to have a more complete understanding of when this happens. So the conclusion would be clear. We would be done. Because, you know, for a split Azumaya algebra by elementary Morita theory, there's an equivalence between modules of that Azumaya algebra and coherent shapes. So because of the equivalence, coherent shapes is the same as modules over a split Azumaya. Shapes of modules over split Azumaya. And here, it's easy to see that under this equivalence, so or with the trivial, in our case, or X with the trivial connection would go to or X. And so just transporting the X by this equivalence, we would get the Lineage isomorphism. So Lineage follows from applying the equivalence. What happens in reality is a little bit more complicated, but so August Vologodsky, they show that under the above condition, the Azumaya algebra splits on a divided power neighborhood, PG neighborhood of X in T star X, and that suffices. But that will not play a role for me. Turns out to suffice. So my actual well, okay, I will pass to my example in a minute, but before I just want to make a general comment. So okay, so to summarize, so here we everything was based. So we used that again, this Hodge cohomology of X. So it's X from maybe just unraveling a little bit this quite elementary thing that I mentioned without explaining. Okay, so this is of course the same as our gamma of what? Of local or home from or X to or X over G star X. And this is easy to understand, and so under this condition, so this is actually turns out to be isomorphic to direct sum omega I X of minus I. So basically we have this Hodge thing, we have forms sitting in the right degrees. But in fact, well, the forms also appear in a different way via the Hochschild-Constant Rosenberg theorem. Namely, if I compute the derived tensor product, then I will get nothing but, so sorry, it's in a sense a dual setting. Yeah, so sorry, so yeah, so then it will be the sum of omega I x shifted by I, so sitting in the negative degree. And this will play a role for me. So so in this modern terminology, people call this the a modern name is this small loop space. So here x, the relative spectrum of this shift of the G rings is x times x over x squared. Derived product. Where the intuition is that the loop space, the name loop comes from the fact that, you know, you can glue S1 from two segments identified in 2 points, and that corresponds to considering like two factors and multiplying them over x squared. But so, okay, whether the name, you may or may not like the name, but so there is this way to the forms appear. Okay, so we'll actually work with, so we are interested, so in specific examples in X equal to Gmod B, G is a reductive algebraic group. So first observation, which in my old paper with Mirkovic and Romanian, that this Gmod B and more generally Gmod P spaces are well, dream the linear Z spaces, if that's, if you like the name. In other words, that for X equal to Gmod P, the above Azumaya algebra does split on the formal neighborhood of the zero section. So if you want to prove the linear Z, run the linear Z argument, in this case, it's kind of greatly simplifies. Okay, and then so this yeah, maybe I will fix a notation. So this may be omega of x. So also omega of x arises in the following way, which I will, the motivation for this construction, I'll say in a few minutes. Okay, so So first of all, recall that if we have a good, in a good quotient situation, you have an action of X, have an action of an algebraic group on a variety, then when you when you quotient the variety by the group action, then you can trace what happens to cotangent bundle. So it's so this is the Hamiltonian reduction. So this is mu inverse of 0, where mu is the moment map modulo G. And okay, so it's definitely true in an good quotient station when you have a G bundle of the quotient, when X is the total space of a G bundle of the quotient, and in more general, situation, if you think of the left-hand side as a quotient, about the quotient as a stack, then this should be considered as more or less as a definition, where again, when you take the moment value, you should do it in the derived geometry framework. So you can, as you see, you can split it into 2 steps and perform each one separately. So we can also, so this is a composition of two steps. Well, just let me just, for convenience, I'll just say like mu by G is, I mean, maybe it's a silly notation, and yeah, for taking quotient, don't need a separate notation. And so, so we can do the following. So consider in the above setting, we can consider, I mean, we have Gmod, of course, B is a barrel, but if B is T times U, so U is maximal unipotent, then we can take the following. So we can take T star of Gmod U and then, well, here we have an action of Cartan and of G, but so we do the following. So we quotient by the Cartan, and I can and take the moment quotient by G. So we don't really quotient, we only take the 0 of the moment. Map, and I claim that this is nothing but omega of Gmod B. So yeah, maybe this I wrote it in a maybe somewhat unfamiliar form. So this is the so-called, I mean, this is when you just quotient by T, it's a space which appears a lot in representation theory. So it's just a pair consisting of barrel and an element. You think of Gmod B as a set of barrels, and then I just take a barrel and an element in it. But then, so this is a familiar space, but then when I take this moment quotient, I mean, take 0 of the moment map, I recover something truly derived. Yeah, so this is, and just elementary calculation. So essentially this follows from the fact that B perp is U. From that you can quickly see this. Okay, so there's a strange construction leading to the same answer. So motivation is comes from the following. This comes from representation theory. So the following theorem. With co-authors is that, again, P is sufficiently large, and then there is an equivalence between derived category of G modules, maybe like I'll write 0. So this is modules where the center, with modules with generalized central character. Central character of the trivial representation. I mean, the theory is more general, but I want to focus on this. And a derived category of crystalline D modules. Well, maybe write it this way, with nilpotent P curvature. And then corollary is that using this base change, so although this is not exactly true, it should be not just D modules, it should be modules over the deformed TDU. So I should say D modules on Gmod U, sorry, to make it completely true. And then I'll write T weakly equivariant. So now it's good. Yeah, so combining this with the splitting, we see that so corollary of the splitting is that the right-hand side is derived category of coherent sheaves. Yeah, I'll swap it with fineness conditions. That's maybe okay. Of coherent sheaves on what I call G tilde, because of this supported on the 0 section. And then applying, just taking a base change, we see that, modules of derived category of G1 modules, so this is Frobenius kernel,
sorry, Roman, I can't quite read what's in the superscript of G tilde. What is that? Is that the Fourier stressed?
Yes.
And you mean boundary derived?
Yes.
And all categories.
And say, yeah, I didn't write it down, but say modules everywhere finally generate.
And everywhere coherent.
Yes. And so if I look at Frobenius kernel and then take the principal block, that this is a derived category of coherent sheaves on this derived scheme, which I called Gmodb. So to derive this, I take base change, and so the point is that G1 modules are the same as modules for the enveloping algebra, where you kill the so-called P-center, Frobenius center. And that corresponds to taking, killing this Frobenius center corresponds to taking this zero of the moment. Okay, so so here are some well, a quick application is that yeah, sorry. So then there is a next theorem which is not quite written, but I think we know the proof is that we can sort of enhance this, and so that it derives. So it's nice to understand modules over G1, but people really want to understand modules over the algebraic group itself or over higher Frobenius kernels. And so the idea is that we can just do the equivariant version of the above thing. And yeah, really here, maybe, I mean, I was dropping it sometimes, but maybe I should keep it here. So this is equivariant coherent sheaves under G Frobenius twist of omega of Gmod B1. Of GR modules block is G coh. Here it's becoming a little bit awkward, but that's okay. So it's a GR minus 1, 1. Okay, and so the point of my telling you this is basically to discuss some additional structures on these categories that one can observe this way. I mean, there are originally this localization theory was motivated by numerical questions, understanding the most basic form, say dimensions of classification, dimension of reducible representations, as well as conjunction ballistic. But here, I mean, I'm taking it in a different direction and just trying to understand the relation to derived geometry. And so, yeah, maybe I'll just mention one application.
Sorry, Roman, before you do that, could you just clarify what you mean by Gmod block? So you take a category of all rational...
I just take the block, the principal block. So
all rational representations of algebraic group G, is that what you mean?
Yes, but it's known, I mean, if you say you read Janssen's book,
yeah,
then it explains this linkage principle, which says that the category splits into a sum of blocks indexed by, you know, orbits of affine Weyl group acting on the weights. So
my question wasn't about that. It was about what you meant by Gmod. You mean all representations?
Yes, yes.
All rational representations. Thank you.
And yes, block means principal.
So the information is carried in the G equivariant structure on the right-hand side somehow. That's the idea. Okay.
Well, you can maybe say it this way, that we kind of, well, the G of course fits into this exact sequence. So G goes to 1. And so we kind of traded the G1 action for something geometric, traded the action of this small group for something geometric, and kind of the rest goes along for the ride.
Sure, I see.
That's what happens. But it's still useful in this one. Yeah, so there's some application to understanding say cohomology of GR, but maybe it's, I don't have that much time, so maybe I'll skip that for now. But what I want to talk about is the different picture. So this connects to well, things in geometric Lagrange. And so I will need to introduce the corresponding object. So we take the G check, the Lagrange dual group, over some field, possibly, yeah, let's just say over C. And so we can form, as usual, the loop group, G of T. It contains the, or maybe if F is C of T, or which is contains, yeah, I'll call this GF, and then it contains G or, and then this contains Iwahori, so the kernel of G or, not the kernel, but the pre-image of Borel goes to B under the evaluation G order G, evaluation 0, and it contains, well, I0, the pro-unipotent radical. Okay, so there is a celebrated theorem, which in this form is due to Markovich-Velanin, although there were important precursors by other people, Lustig, Drinfeld, and Ginsburg in particular. So it says that representations of G is equivalent to the category of perverse sheaves on the affine Grassmannian. Equivariant in respect to G, or where affine Grassmannian is, of course, the homogeneous space GF mod G1. So this is a so-called geometric Satake equivalence. And so there are further things to say here. So then there are some, so there's derived Satake, which which says that if you consider the derived category, then this is well, derived category of equivariant. Yeah, of course, here it should be the dual thing. One derived scheme, which can be, well, maybe since I already introduced this notation, so let me write it this way. So omega of G, and then it will be G times G. So this is really, I think the idea goes back to Drinfeld, but in characteristic P, in characteristic 0, it appears in my paper with Finkelberg. And there were some unpublished contributions by Gasgary and Lurie. And in characteristic P, this is a in progress with Demarinkin.
So could I just clarify that in those two statements, G is a complex group now, or is it still?
So the dual group is complex, but the right side, so the dual group is complex, but the coefficients.
Yeah. So,
I mean, it's perverse sheaves with coefficients in K.
Mm-hmm.
So that's this, I think. And then another theorem is the so-called Finkelberg-Merkovich conjecture, which is again theorem in progress with Simon Risch and Laura Ryder. It says that the category that we care about, I mean, that we talked about before, that representation theory of G block is equivalent to perverse sheaves, which are I0 equivariant on the Grassmannian. So this is, yeah. Okay, so basically the actually interesting thing here is various structures that can be seen on the two sides. So I think I have like 1 minute left, but so I'll just make a few remarks. So first, the derived Satake category monoidal category acting on derived category of I0 equivariant sheaves on Grassmannian. And this can be recovered. So these coherent descriptions can see such an action in the coherent description. And then, okay, so interesting things to understand. so-called S1 action and S1 localization on the two sides. So I'll just name the names. So in characteristic 0, this was discussed by Nadler Ben-Zvi some years ago, Ben-Zvi Nadler. And here in characteristic P, this is should be closely related to the recent works to so-called Smith theory, which is localization, maybe German's Smith theory. So this is the particular form of localization to fixed points in the modular coefficients setting, and also so relation to cohomology of Frobenius kernels, which are, in some form understood by Friedlander Sussman. And this is related to, not to, so there's S1 action, but then there's also this determinant bundle on the Grossmanian and its characteristics classes. But yes, I think I don't quite have the time to discuss the structure, so I'll stop here. Thank you.
Okay, thank you very much, Roman. Are there any questions or comments?